So this is the Climate Science and International Perspective panel. And on our panel, we have Marcel Croc, he's the director of the Clintal Foundation. We have Ronan Connolly from the Centre for Environmental Research and Earth Studies, and Tom Harris, International Climate Science from Canada. So they're each going to come up and speak to you for 20 minutes at a time, and then we're going to take some questions. So because the person that's been nicest to me out of the three of them is Ronan Connolly, he is going to come up first. Thank you very much.
Okay. Okay, do we have my slides? Okay, okay. So if I was doing this outside of America, I'd call this uphill football, but I know football here is different. And so I'm going to be talking about how when you are doing science that goes against a paradigm, it is like playing uphill soccer. It is like if the goal that you are trying to score in is at the top of a hill. And if you're going along with the narrative, the goals are at the bottom of the hill. So otherwise, the rules are the same. So what do I mean by paradigm and going against it? So Thomas Kuhn in the 60s, he was looking at the history of science, and he's going back to Kepler, Galileo, all the way up to Einstein, and he noticed that there was patterns in how science progressed. And he noticed that most science is where the scientists will be following what they learned in their textbooks or what they learned from their tutors and their teachers. And he called that normal science. And he called the science that they were doing would be a paradigm, a scientific paradigm. And so he noticed as well that normal science would be criticizing anybody that was questioning those paradigms, but also he noted that most of the big advances in science occur from the mavericks who identify the anomalies in the current paradigm and come up with a replacement paradigm. And that's the ultimate progression that he was finding. So before we get on to uphill soccer, we should talk about regular soccer, which is the current academia system. And the big problem is, if you are a professor or a senior lecturer in an institution, you spend a huge amount of time writing grant applications, and it can take up to a month or 2 months, and studies have shown about only 1 in 5 grant applications are successful. And so the people who are succeeding getting them, and that gives you 3 or 4 years, and then you have to get another one. So people who are looking at it say, well, you've got to mention the right buzzwords, climate change, diversity, AI, whatever the topical ones are. It needs to be new, but not too new. And so that's how you get your funding. And it lasts you 3 or 4 years. But then you get your funding, you do your science, and then what happens at the end, you try and present it to the public through publishing in a peer-reviewed journal. And what's that? Well, what happens is you submit your article to a journal, the editor identifies 2 or 3 scientists working in your field and asks them, unpaid, can you review this article and say if it's good or not for free? And then once they've done that, the editor makes a decision. And so here's the thing, you then, if you want to get it published, you don't question any paradigms because your reviewers probably agree with them. You just build on existing papers and you hoard in the latest buzzwords. And of course, then the thing is, if you are lucky enough, you finally get your paper, you're left with this. When I get a paper published, I then have to explain to my wife, she says, wow, that journal's published, how much are they paying you? And I say, no, we pay for the journal for the privilege of publishing. It's like, okay. And over time, what we've been finding is, as well, this study is showing that scientific journals are becoming more and more jargon-filled and specialist. And so, they just use the technical knowledge. And the consequences of this, non-specialists are afraid to read journals, scientific articles. They're like, oh, I don't understand that. I don't want to do it. And the specialists will not read papers outside of their field. So it's leading to the over-specialization in science. And so essentially what we've got is replication is discouraged, and only normal science. You're discouraged from questioning paradigms, and the over-specialization of science is a thing. Now, I want to dedicate this talk to my father, who unexpectedly passed away in August. And so, as well as being my father, he was also my teacher, and my colleague and friend and inspiration in how to do this. And so he taught, yeah, thank you. So he kind of led the way in how to do uphill soccer. And what we did is, the two of us, we were working on other projects. We were developing sustainable methods for fish farming. And then as environmentalists, we were saying, oh, everyone wanted to ask us about the environmental problem. And the other thing is, we were looking at climate change, because we were looking at the distributions of optimum fish conditions. Anyway, we just said, look, what is going on with climate change? And we decided to do it for free, just out of our own interest. And we didn't have interest in publishing. So we were basically, what did we do? We said, well, look, each of us would pick a topic, and then the other would try and demolish all of our arguments and our analysis. And it was only when we had finished, we could no longer demolish each other's arguments. So we said, fine, it's stress tested. It took us 4 years, but this is it. So how did this? Well, first of all, we bypassed the funding problem because we did it in our spare time. Okay. We were able to question all the paradigms, and then we saw the problem because we realized that we had found major problems with the existing paradigms. And we said, we'll never get this published, but we need to let the public know. So what we said is, at the scientific community, so we decided, let's put our findings online. We set up the open peer review journal, and then let the public peer review it. Let the scientific community do it. And we also realized that jargon problem. We said we need to explain to the general public. So we did a blog in non-technical language, and both of those websites are still online, haven't been updated in a while, but they're very useful resources if you're on it. So oprj.net, globalwarmingsoft.com. Okay, so just if you watched my talk yesterday, or if you're watching online, you can look at the archives. I was talking about global temperature data, and I was saying, we were finding that this hottest year on record didn't seem to work. So Michael was saying, but if it's not supposed to work, if we're not seeing the hottest year on record, the climate models based on the greenhouse effect theory say they should be. So he said, why not? What's wrong with the models? And he said, the problem with you can't test a model with other models. We said, can we look at real data? And he said, well, there's a weather balloon data. So he decided to look at this. Now, this is a technical slide. Okay, I'm sorry about this, but the weather balloons, what they do is they record temperature, pressure, humidity, horizontal wind speed, and wind direction. Now, because Michael and I both have chemistry, in chemistry, everyone's taught the ideal gas law, PV equals nRT. So some of you may be familiar with that. And Michael realized, hang on, we're recording the temperature and pressure. If you divide P by R times T, and R is a constant, 8.3, that gives you N divided by V, which is the molar density, the number of moles per cubic meter, which is basically the amount of gas per cubic meter. And he said, I wonder what happens if you plot that against pressure. And so what he realized is, as you go up in space, up towards space, obviously the air is less dense, so it should fall off as you go up from ground to sky. And sure enough, it does fall off. But he went and he said, wait a second, it falls off as a straight line, but then there's this point and it changes the slope, and it's a different line. And it turns out that's the tropopause. And we said, oh, that was just one balloon. No, we looked at it. It's always in the Arctic, everywhere. It's just the exact point change of slope occurs at different places. So this was a video, or this is if we gave a talk in 2019 in Tucson, and so for that we just said, let's pick 1 year of the data here. Now this is the usual way of plotting it, temperature versus pressure. But you see, these are the data points, and they're all squiggly all over the place. when you plot molar density against the pressure, all of those points fall onto two straight lines. Now in science, if you can get hundreds of data points all over the place and get them all to fit onto two straight lines, then you know you're onto something that's fundamental. And it doesn't tell you what fundamental it is, but it tells you that we have something. So we then said, well, what happens to these others? So we analysed all of the weather balloons we could find that had enough data. So it was 13 million. And we found pretty much everywhere has that same effect. And there's only some slight exceptions, which is basically polar winter and tropical monsoon sands. And we don't have time to go into it, but you can read the papers to find out a little bit about it. But what we did is when we accounted for that change in phase, change in slope, and changes in humidity, we found that for any balloon, we were able to explain the temperature profile from ground to where the balloons burst in the mid-stratosphere in terms of the bulk gases. So that's nitrogen, oxygen, argon, and water. And we didn't have any room for the greenhouse effects, or, for the trace gases, which is what the models were saying should be the main one. So anyway, we published those, and we did 8 papers in all. But then what did we do? We said, well, let's email all of the scientists in the ones working in the field for getting communication. We had our blog, got a lot of interest and attention, and so we got a lot of commentary and discussions going on. We were, in our spare time, when we had holidays, we'd try and go to somewhere where we could meet the research labs in the different places. And then we also would Skype scientists for collaboration. And so because by doing that, we were actually able to, we realized if you only question 2 or 3 paradigms at a time and you do it diplomatically, it is possible to get publications. It just takes a lot longer. So we got these 3 papers published in peer-reviewed journals, but we were like, this is taking a lot of time in our spare time. And so along with Willie Soon, we decided in 2018 to set up the Centre for Environmental Research and Earth Sciences. And what we do here is we do science and we follow it where it leads. And if you like what we're doing, then you can support us. And it's like a different approach from doing it. But it means it's not a get rich quick way, It's like if we wanted to get rich from this, we would probably be better doing downhill soccer and going with the grant aided. But the advantage, we can actually follow the science where it leads. And then once we see a topic that's interesting, as soon as we've time, we start on it. We don't need to apply for a grant. And we don't have to stick with it for 3 to 4 years if something new comes along. We can follow it where it leads. Now, this has led to, basically, we can do science, okay? So just these are the rules of uphill soccer. Only 2 or 3 paradigms at a time. And it's, and this is it. But also, as soon as you get published, people are going to just try and ad hominem and use lie and cheat to try and get it in. But we have been successful. So far, 44 peer-reviewed articles across a whole range of topics. And one of the key bits we've done is we've actually led multiple international collaborations. And so far, we've had 174 co-authors. And, yeah, okay. And if you saw the talk I gave yesterday, we were discussing this topic, and we've had a range of different people, co-authors, some who agree with us, our fellow climate heretics, like Marcel over there has contributed in a couple of them, but we also get with IPCC authors, we look at a whole range of perspectives because you can collaborate with scientists. You don't have to agree with them on everything. That's okay. That's how science works. We also have looked at, there's a paper on looking at COVID, temperature homogenization. We look at different topics, and you can see we've had, over the years, we've had more and more collaboration. So this aspect has been very successful. But I want to finally, so if you like what we're doing, this is the stuff. But I want to show, ultimately, going back to Michael's work with the weather balloons. And this has been a slow burner because we realized early on that what Michael was discovering has too many paradigms for one paper. And we realized we could not get it published, questioning all of the paradigms, so we had to do things piecemeal. We just had to say, let's just do one bit, we'll just question 2 or 3 paradigms per paper. And the first one we said, well, can we at least get people looking at the molar density? Because that's relatively easy to do. If you have high school physics or chemistry, you could probably do the analysis in molar density. We said, okay, once we do that, we said, but it needs to be new, novel. And so Willie pointed out, maybe you can look at the relationship between the tropopause and the troposphere using this thing. And so that's what we did. We said the use of molar density anyway, we submitted that to a journal, went through 4 rounds of revisions, and finally the editor-in-chief went and recommended publication. And so we were like, oh great, we were just about to celebrate, and then we found out that the journal had rejected. Is there no sound on that, is there? Should be sound on that clip. Anyway, it doesn't matter. So the editor-in-chief was like I was saying, okay, this is ridiculous. He'd never seen that in his whole career. And so we asked him, could you write a letter saying this? And he did. And so we then reached out to another journal, an editor, and said, look, this is what we went through. Can we expect a fair hearing from your journal? And he said yes, and so we submitted it. And he actually did give a fair hearing. And we got 2 decent reviews back, but both of them he said, oh, this is very exciting results, but why are you using molar density? Nobody's ever heard of that before. Why don't you just use the regular definition of the tropopause? And the editor said, oh, you could probably get that, that's fine. But we were like, well, we're showing the molar density gives a much cleaner definition of the tropopause, and we want to get people to using it. So we said, fine, we have to actually take a step back. So we said, let's look at a different use for molar density. So what we did is, I don't know if you're familiar with it, but if you're studying, there's a lot of these paradigms related to the atmospheric circulation. Up until 2021, if you wanted to study atmospheric circulation, you needed to use wind speeds or you needed to use theoretical models. And so what we said is, but hang on a second, if you didn't know how much, if you are measuring the wind speed at 500 millibar, you don't know how much of the air is moving. So, but we realized if you multiply the molar density times the average molecular weight of the air at that point, you can tell the actual mass flux, the amount that's leaving, moving back and forth. And this is very useful. And we were saying, oh, this is great. We can use it for looking at all of the atmospheric circulation, theoretical models and the paradigms. And we were working on this, and we said, well, let's just start with the main ones everyone looked at. And we should be able to show how we're just looking at the horizontal component, but we should be able to look at the Hadley cells and just analyze them. And then the problem was that when we tested this, we were finding that they weren't actually, those paradigms weren't able to explain the observations. And so we were like, oh, well, we can't question the Hadley cell. We're already questioning 3 paradigms. We don't have room for another. So we said, okay, we won't hide from it. We'll hint at the implications. We'll say, this might be of interest. Dig here for the thing. And when we did that, yes, we got that. So there's no sound on these video clips, is there? Okay, anyway, there should be, but it doesn't matter. It's just cheering. So that's, okay. So we decided, okay, that's great. We'll do a more detailed analysis of the Hadley cell in later papers. But we said, but we want to go back to that 2019 work and to look at the definition of the tropopause. And so what we said is, okay, let's look at the different definitions. And we said there's actually multiple definitions of the tropopause, but they're all describing the same thing. It's like the blind men trying to describe the elephant, and one's holding the tusk, one's holding the tail, and they each think they're describing something different. They're the same thing. And what we said is, it seems the molar density is the most fundamental aspect of that. So we went and we presented our analysis, and we got we got it published in a conference proceedings, and we were told to submit, the journal organizers said, oh, you can do a more detailed thing. We're doing a special issue on this conference. And so we were like, oh, this is great. So we went through several rounds of revisions, and then it was rejected. And then we said, okay, let's submit it to a different journal. And we submitted it, and then we got a desk rejection. They said it didn't even send it out for review. They said, oh, it's not new enough. But we persevered, and eventually we got it published in another journal. And so now we are in a position to go back to the 2019. This is our thing. And so I just want to say that it's very hard that Michael isn't here with us, because he set this, but he has set this up for CERES, and that's supposed to be Willie there. We're gonna try and follow up on, and we think he has set this goal up for us in the next thing. So just to wrap up, I just want to say ways that you can support us. So go to www.ceres-science.com. And you can, first thing, you can sign up for our mailing list. And so whenever we get a new press release or new story, you'll get notifications of it. We also have a YouTube channel and a Rumble and things like that, so you can subscribe to that. And go to our archive and look at all of the different stories, because we've quite a number, right, Willie? A number of stories. If you are like to look at the actual technical details, go to our publications. And if you are writing your own papers, cite us. And then finally, you can support us. Okay, thank you.
Thank you so much. Thank you, Dr. Connolly. Thank you.